Okay, now we are trying to discuss the fourth question. Two vertical parallel plates are situated 2.5 centimeter apart in a vacuum. The potential difference between the plates is 350 volts. An electron is initially at rest close to the negative plate and in the uniform electric field between the plates. Calculate the electric field between the plates. Calculate the electric field between the plates. So this calculating the electric field is usual. The voltage is given. So the voltage is given. So you apply is equal to V over D and you find the electric field strength in Newton per coulomb they have given, or you can give it in volts per meter. Then show that the force on the electron due to the electric field is this much. Again, you can use the second equation. We have force, the electric field strength is equal to force over charge. So force is equal to EQ, and you have this value 2.24 times 10 to the power minus 15 Newton. The B part is the different one. The electron accelerates horizontally across the space between the plates. Determine the horizontal acceleration of the electron. So now what happens here is there is this parallel plate. This is the positive end and this is the negative end. And there's an electron closer to the negative end. So you can see that the field is going to be in this direction. I'm not drawing all the field lines, I'm just drawing the direction of the field. So a positive charge moves this way, so a negative charge would move this way. So the electron would feel an electric force in this direction. The question says the electron accelerates horizontally across the space between the plates. Determine the horizontal acceleration. So everything that they are asking here in this part is the horizontal one. Why? Because there is also the force of weight acting vertically down on the electron. The horizontal force is the electric force, but the vertical force is the weight. But since they are only asking about the horizontal, we don't have to worry about the weight. In fact, that is the last part of the question. So since we are talking about the horizontal motion, we don't have to consider the vertical motion. It is like the projectile, in which you can treat the horizontal motion and the vertical motion separately. And when you're discussing about the horizontal, you can forget about the vertical totally. And when you're discussing about the vertical, you can forget about the horizontal totally. So two directions which are mutually perpendicular can be treated independently of each other. Thank God. Okay, so they're asking you to calculate the horizontal acceleration. A force is given and they're asking about acceleration. So obviously the equation that should come to your mind is F is equal to ma. The force, so acceleration is equal to force over mass. The force we calculated from the earlier part is 2.24 times 10 to the power minus 15 Newton divided by the mass of an electron. You have to look at the data. 9.1 times 10 to the power minus 31, and this gives you an acceleration value of 2.46 times 10 to the power 15 meters second minus 2. Then the next part of the question, they're asking you to find the time for the object to travel horizontally, just like the projectile motion. But sorry, it's not projectile motion, guys, be careful, this is not very similar. I brought the example of the projectile motion to show you how two directions which are perpendicular can be treated independently. This is not similar to projectile motion because there is initially zero velocity and the forces act in both the direction. If it should have a parabolic path like a projectile motion, there should be an initial velocity and there should be a force only in the perpendicular direction. There should be an initial velocity and a force, weight, only on in the perpendicular direction. Here the forces are in both the directions, so this is not going to follow the projectile path. Okay, so this is not projectile motion, but the idea of treating the two directions independently is something common to both projectile and this case. So if you look horizontally, they are asking you for the time. So we're going to use the equations of motion, obviously. So let's go with that. S, do we know S? Yes. So do we know S? Yes. So 2.5 centimeters. Then U0, we don't know, and A we just calculated 2.46 times 10 to the power 15 meters second minus 2. So we don't know the V value, so we need an equation without V. So I'm going to apply S is equal to, oh my god, S is equal to ut plus half at squared, the only equation without V, and I'm going to apply this equation in this direction, considering the left side to be positive. Now don't be confused of this arrow as a field line, this is just the direction of the equation when we apply a vector equation. So yeah, so 2.50 times 10 to the minus 2 equal, this is 0 ut plus half times, okay, so 2.50 times 10 to the power minus 2 equals 0 plus half. A is this much, so 2.46 times 10 to the power 15 times t squared. Do the math and you will land in an answer. T is equal to 4.5 times 10 to the power minus 9 seconds. Now I have a question here. Now this is a t squared, so when you find the square root, you would get two values, the plus and minus. Now minus is not possible because it is time, so we get the positive one. The C part of the question, explain why the gravitational effects on the electron need not be taken into consideration. So as I said earlier, the gravitational force and the electric force are mutually perpendicular to each other. So hence we can treat both the forces independently. Now it is quite confusing because the idea that electric force and gravitational force are perpendicular looks like only one point, but if you look at the mark scheme, it is that one point which scores both the marks. So this one point scores both the marks. Gravitational force, either gravitational force is normal to electric force, or electric force horizontal, or gravitational force vertical. So there's only one idea, but if that one idea is given both the two marks, because I think there's nothing more to say. Now some people out of habit would have written this idea that electric force is smaller than the electric force is very greater than the gravitational force. Yes, that is true. Electric force is very greater than the gravitational force. Yes, that's true, but that is not the reason why we neglected the gravitational force. In fact, here we didn't neglect it, we simply didn't make use of it. It's not that we have assumed that there is no weight. We are not bothered whether there is a weight or not, because it is in a perpendicular direction. So we are not assuming the weight to be zero, we are simply not concerned about it. If the situation was like this, look here, if the plates were like this and the electron was here, then if you look at the electron, there would be an electric force upward and a gravitational force downward. Now both the forces are on the same line of action. Now during a calculation, if you want to ignore if you want to get rid of mg, and if you assume mg to be 0, for example, in this situation you're trying to apply F is equal to ma, and instead of putting the resultant of F electric and mg, right, rather than writing F electric minus mg is equal to ma, if you simply write F electric is equal to ma, then you are assuming mg to be 0, or mg to be comparatively smaller than the electric force. Yes, when they're acting on the same line, then to get rid of mg we can use the argument it is very small and we are ignoring it. But here we are not ignoring mg. Mg is there, like it or not, but we are not bothered because it is not bothering us. It is happening in a perpendicular direction. So if you ask me, I would say this idea should not even be given 1 mark. So they are giving at least 1 mark, but I would say not even give that 1 mark.